right, good afternoon. I think it's time to start. So it's really essential that you see the source code because there aren't going to be any slides during this 1-hour talk or live coding session, whatever you call it. I'm just going to be showing you the source code, just as runnable source samples. You can find all of the code you're going to see here during this talk on GitHub. So I encourage you to have a look at it and play with it a little bit. That's how we're going to explore the Hystrix API. So I guess we're ready to start. The code is visible for the last row. Okay, please nod your head when you understand something. I will be asking whether you understand everything because I want this talk to be really interactive. So if you have some questions, be encouraged to ask them, and we're going to explore a little bit, try out a little bit, and see how the library actually behaves. Okay, so let me tell you a little bit about this piece of code. Coincidentally, I start very similarly my previous talk. So this is like the simplest thing you can do in Java. This is actually groovy, but doesn't matter. So I'm going to the internet, I'm fetching a little bit of data, and I'm doing a string out of it. So it's a crappy test. It doesn't really test anything, but that's not the point. So what you see here is just some random piece of code that goes over the network, fetches some data, and presents it to the customer. What's really the problem here is that it can fail in numerous ways. You can have a network connection down. It can be terribly slow. You can have problems with DNSs, so on and so forth. So what Hystrix does is it tries to shield you from the issues with the actual surroundings, so that if one of your collaborators, the systems you depend on, for example, example.com domain, if you rely on someone and this second party has some issues, it's down, it's slow, or something even worse happened to it, Hystrix tries to protect you from it so that the failures of the systems that you depend on do not propagate to your system. So your system does not become unstable just because some other system became unstable. So how can we protect it? So the first thing we can do, I just had a talk about completable futures, so let's start in a very similar fashion. The first problem, and this one is actually the most terrible one. So you might think that when your collaborator doesn't work, then this is the worst thing that can happen. But that's not the case. The worst thing that can happen is that when your collaborator works, but it's just much slower than usually. Because in that case, your application becomes slower. If your collaborator fails, then that's fine. You just propagate the exception or handle the exception. But if your collaborator if it takes like a minute for your collaborator to return, for example, with the SQL query response, where it used to be 100 milliseconds, then that's a real problem. So the easiest thing to do is that you can actually take your code and wrap it in a callable. So I mean, we're all experts, so I'm not going to explain how it works. I'm just taking a bunch of code. It can be a lambda expression in Java 8. So I'm taking a bunch of code, wrapping in it callable, and putting it in a thread pool, like here. Then I get a future, and I can wait up to 1 second for that future to complete. Now, there is a problem here. So this future has 10 threads. And now imagine one of the systems is actually, the task you're executing is much slower than this 1 second. So it takes like a minute or so. So quickly, you will saturate these 10 threads in a thread pool. You're just submitting 10 tasks, and all of them are stuck in a thread pool, and nothing happens. So what happens from the client perspective, from this code's perspective, if you have a very slow task, you submit it to a thread pool, but the thread pool is already like saturated with all the other tasks running. What happens next with your task? Yes, but not in this particular case. So by default, if you look at this piece of code, and this is like the thing that you see always in every single Java tutorial, by default, an executor service creates an unbounded queue of tasks. So let me explain you how the executor service works. I can actually inline this guy, or I can't because it's groovy and it's crappy here. So I can actually replace this guy. The inline really doesn't work? Nope? Okay. So this one actually creates this. I just inlined it. So I have 10 threads here, 10 threads here, and this is the crucial part. So it creates an unbounded queue of tasks. And every time you submit something into a queue, you're actually first putting it, submit something into a thread pool, you're actually first submitting into a queue, and then a first idle thread, the one that doesn't have anything to do, takes a task from that queue and executes it. So if you have a system that you're collaborating with, for example, example.com, which takes an enormous amount of time to respond, then what happens is that you will saturate all the 10 threads you have in a thread pool, and then you start to build up tasks in this queue, because this queue is unbounded, so you're going to have more and more tasks waiting for a thread that can execute the task, but this just never happens, or it's way too slow. So this task just keeps growing and growing and growing, and guess what? You have a system that is perfectly healthy. However, the system it depends on, example.com, or it can be a database, it can be a web service, it can be an SMTP server, pretty much anything you contact over the network, because that introduces a risk of something going bad. So pretty much anything that you collaborate with, if it becomes unstable, you become unstable as well. And guess what happens? You get out-of-memory error at some point. So your application looks as if it had a memory leak, or as if it had an enormous load, while in fact it's the other system that has problems and your application is completely fine. So this is one of the things that Hystrix actually tries to solve. What happens next? This one actually misses, and I actually summarized them here, actually misses quite a lot of stuff that an enterprise solution should have. So you have no metrics. You don't know how many threads are utilized. You don't know how long is that queue. This queue is unbounded, so we should actually change it into something like, I don't know, does this one have a parameter? Yeah, this one has capacity. I'm not really sure whether it does what I think it does. So we're missing metrics, but there's one important and really clever thing that we can actually do. So imagine you're calling this external system, example.com, your database, whatever, and for the last 10 seconds, it always failed, or 90 out of 100 cases, it was always failing. So you can rather safely assume that no matter how many times you're going to call this external system, it's still going to fail. It can fail with an exception, or it can fail with a timeout. So there's simply no point in keep calling it, because it's just having a hard time. So what's the point of calling it over and over and over again if it fails? At the moment, maybe it will become healthy in 10 minutes, or maybe just half a minute, or maybe after 2 days. Yet, we should apply a heuristic here that if something is broken, we should not try to constantly poke that system, because it won't really help. We just have to wait a little bit and just stop calling it for a second and just fail fast. And this is actually a known pattern in engineering, failing fast, and it's implemented in Hystrix in the form of a circuit breaker. We'll get to that later. But the idea of a circuit breaker is that you don't call a system that is unhealthy. You just fail immediately and hope that it will become healthy in a second. Everything clear so far? Are you still with me? Cool. So let's do the actual Hystrix. So what you saw here was wrapping a block of code and putting it into a thread pool. But how does it change if you go for Hystrix? Actually not much. So this is the same piece of code, nothing has changed. However, we are not wrapping it in a callable, but we are wrapping it into something called a Hystrix command. And this is part of the API, it's not big. So a Hystrix command has a name, it has a group. We will discover various parameters of this constructor in just a few minutes. What we need to know right now is that the piece of code that we suspect can be somewhat dangerous, and by dangerous I actually mean it can fail, like throwing an exception. It can take quite a long time to complete. It fails very often, and so on and so forth. So everything, the heuristic is that if it goes over the network, it can probably fail because it's a different computer. Locally it can fail as well, but it's less likely. So we have a command. It's just a class. And then we go for the actual Hystrix. So this is really, really simple. We create an instance of this class. Of course, we can pass some parameters like whatever we want here and get some instance fields here. This is totally possible, and you're going to use it in practice. But for the moment, the constructor is empty. And what we're doing is that we're basically saying, OK, this is my command. Execute it. And everything we talked about in the previous slide applies here. So we have timeouts. By default, the timeout is 1 second. You have a bounded queue. You have tons of statistics. We're going to look at them in a demo in just a second. You have circuit breaker, so this mechanism that we'll see how it works during the live demo, and tons and tons and tons of other features that an enterprise-grade solution, sorry for using that name twice already, that a solution running on production should have to be stable. So this one is guaranteed to return within 1 second. That's a default. And it adds a lot of features that you're going to see in just a second. But as you can see from the client perspective, it's really simple. It's actually even simpler than a thread pool because there is no explicit thread pool. However, every command in Hystrix, actually every command group, but that's just detail, has a dedicated thread pool. So there will be a thread pool for this command, and if we have a different type of command, there will be a separate thread pool, and all of them have by default just 10 threads, but obviously it's configurable. Any questions? Yeah, sure.
What about those thread pools in the context of, say, WebLogic application server? How to connect thread pools of application server with Hystrix?
Okay, so luckily I never used WebLogic, but it's completely agnostic. So whatever the thread pool in WebLogic is for HTTP, for EJBs, whatever, you don't touch them at all. The Hystrix has its own thread pools, it manages its own thread pools, and you have little control over them.
Right, but this is the issue because WebLogic manages the resources of the server of your machine, and it can predict resource consumption. And in this case, you're putting the size of your threads running in Hystrix. You don't see them in the whole.
Yes, but that also means you cannot use any explicit threads at all. You have to interact with WebLogic API or something, right? Yes. However, from the management perspective, actually, I haven't seen WebLogic, but I'm pretty sure Hystrix has better monitoring capabilities than WebLogic. And bear with me on that, because it has some really awesome stuff coming in. Okay, so just be patient. Okay, so I said that every command has a default timeout of 1 second. This is obviously configurable, so this is the same command as we saw just a couple of seconds ago. However, this time I explicitly set a timeout to be 5,000 milliseconds. This is just one of literally dozens or hundreds of parameters you can pass here, but just keep with me on that one. So this is really simple. And if I actually execute this command, I have no idea what's going to happen, but it can either succeed or fail. It succeeded if the timeout was shorter. Again, I think I'm just going to example.com domain and fetching the contents of their website. So with 100 milliseconds, it's not enough, and I get timeout exception. But that's like too simple to demonstrate. Okay, and one last thing before the actual demo is fallback. So very often you don't really require a dependency to exist without even thinking about it. So there are things that you connect to, but if they are not available, if you make a request to that service and it's not available, it's not a big deal. You can just display an empty box on a user interface, or you can just have a small label saying that your personal recommendation is not available at the moment, so here are the best sellers. So this is what fallback is all about, and the concept is so simple that I won't even bother explaining it that much detail. Pretty much, if the command fails, rather than propagating an exception, we return a fixed value or some fixed response or whatever. So it's like a try catch and returning something from catch. So there's not much to explain here. Okay, so now I'm actually going to show you some demo. How many of you understand what's on this part? Do you like kind of recall what's going on here? Just briefly, it's a Spring MVC or Spring Boot application with a single controller. It's a REST service, right? And it has two endpoints. One is called unsafe. And the reason it's unsafe is because I'm calling some external service. I'm passing a bunch of parameters. I will explain them in just a second. And that's it. So I'm calling this external service directly without any decoration or without any extra layer on top of it. And the reason it's unsafe is because the external service, it's my class, it's sort of like a mock, and it takes a bunch of parameters. And these parameters are duration and error rate. These are the two that are interesting. So I can actually control by passing a bunch of parameters to this REST endpoint or this web endpoint. I can control how long this service will respond, for how long the service will be responding. So I can simulate that the system I'm calling is really slow. And more importantly, I can actually control how often this external system will throw exceptions. So without further ado, I'm actually starting the application right now. And in the meantime, I'm going to explain the second endpoint. So it does exactly the same thing. The application is just started. Yeah. So application already started, and I'm going to show you the second endpoint. So the second endpoint does exactly the same thing. It calls external service, so the one that's potentially risky or potentially unhealthy. Our application is okay. It's the external service. It's always the external service. That's not correct. But what we do is that we're wrapping it in a Hystrix command, and we're invoking it. So this is pretty much the same thing. It's like submitting into a thread pool and then doing .get on a future. It's like executing this piece of code, however, with all the Hystrix machinery surrounding it. And you'll see in just a second what does it actually mean. And again, we have a full control over how this external service behaves. So we can simulate that the service is slow, or we can simulate that it's, for example, throwing exceptions really, really often. Okay, so the application is already running. So let me run a simple test. So I'm going to call it right now. And the endpoint was unsafe, right? So that was the first one. Calling this endpoint, and what I get is OK, because that's what we return from the endpoint. So that went well. I can actually call it multiple times, and every single time I get OK. So that's fine. Our external service works, and our service works. What I can do now is that I can add these parameters. So remember, the first one was duration, and the second one was, as far as I remember, error rate. So if I go for duration of 1 second, and now look now, I'm pressing enter. I have to wait about a second, and then I get OK. So you see, I'm actually simulating a system that is relatively slow, because it takes a second to respond. But what's even more interesting, I can also add, let's make it 100 milliseconds, I can add a second parameter called error rate from 0 to 1. And if it's, for example, 0.8, it means that we are simulating that the external system, the one that I'm calling here, the external system will throw an exception in 80% of the cases. So 8 times out of 10, I'm going to get an exception calling this service. So let's do it right now. Making a request, and what I get is internal server error. Let's do it again. Internal server error, internal server error. I should get OK one day. Damn you, statistics. OK, it should definitely be OK, but it doesn't really matter. I can just reduce the probability, you know. OK, now it's OK. Are you still with me? So we have a simple REST controller, and we are calling some simulated external service that doesn't behave really that well. Do you know a tool called AB? Like this one. AB comes from Apache Bench, and it's like a JMeter for command line. And if you don't know JMeter, it's a load tool. That's it. So it has pretty much just 2 interesting parameters. Well, apart from the actual URL, so I can call the unsafe endpoint with a duration of 100 milliseconds, which means every request will take on average 100 milliseconds. And I have 2 parameters here. Do you see the terminal? I can increase the font a little bit. So it has 2 parameters. The first one is the number of requests, and the second one is the concurrency level. So how many concurrent threads are there going to be executed? Let's say 5. So we have 5 concurrent clients, and all of them will try to execute around 200 requests to make it 1,000 in total. So I can run the simulation immediately, and you can actually see the progress right now. I'm just going to chat for a little bit. So what kind of the result do you expect? We're executing 1,000 requests, and every single request will sleep for 100 milliseconds, basically. You're going to get a response in just a second. By the way, be encouraged to answer my questions, because I have these things, which I have no idea why are they for, but I'm supposed to give them to you. So this is the response, and the good thing is that it doesn't even show you the mean value. It shows percentiles. The mean or the average is pretty much useless when you're measuring the latency and throughput in the system. So go for percentiles. And if you don't know what percentile is, the definition is really simple. This line tells me that 99% of the requests were faster than 109 milliseconds, or at least as fast as 109 milliseconds. So there was only 1% of the requests that was slower than 109 milliseconds. That's the end of the definition. So you see that median, which is the 50th percentile, is 103 milliseconds, which means half of the requests were actually within 103 milliseconds. So that's fairly simple, and I guess you should expect a result like that. What's also interesting is that we have no failed requests. And that was to be expected because we didn't set this parameter error rate. Are you still with me? Okay. So now let's play a little bit. What kind of parameters do you want to try first? Let's go for error rate of 0.8. Excuse me? Ampersand, yeah. I'm not really good at computers, so sorry. Okay, so this is the same test, and the external service is written in the way that it first sleeps for 100 milliseconds, and then it can possibly fail. So the response times should be around 100 milliseconds again. However, we should see a little bit of errors. So what happens now? I'm chatting for a little while just to have the test pass, and here it is. So the response times are pretty much similar. They are slightly bigger because the payload was bigger, but I guess it doesn't really matter that much. But this one is important. We have 822 failed requests out of 1,000, which is precisely what to be expected, because the simulated error rate was 0.8, right? We can play a little bit. What do you want to try this time? Come on. Bigger or smaller? Bigger? So let's make it 5 seconds. Okay, this will take a while, so I have to talk at least for 5 seconds so that at least a few requests are actually finished. I'm not sure for how long I was talking. So at this point, there is no Hystrix because we're calling the /unsafe endpoint, the one that doesn't know anything about Hystrix. So the response times will be rather big. It will be around 5 seconds with rather big error rate. So let me just stop it right now. The good thing about AB, even though it's a very primitive tool, the good thing about AB is that I can interrupt it at any moment, and I will actually get a partial result, but there is some result. So I just stopped it right now. You see that 50th percentile, which means half of the requests, were as fast as 5,008 milliseconds, so 5 seconds. And again, 22 failed requests out of 30. Very little requests because they were so long. But the error rate is more or less 80%. Okay, so what else we can try? We can try very small duration, but a lot of errors and so on and so forth. This is really, really fast. But again, we can try it. We can play for a little while. Now let's go for Hystrix. So again, and just to prove you that we were actually executing something, there are plenty of exceptions here in the bottom. So the Hystrix does exactly the same thing. So it calls the simulated external service. However, this time it wraps everything in Hystrix command. And Hystrix command is this magic ingredient that adds all the enterprise-y features. So let's go for /safe this time. And before we experiment, let's go for duration 100 milliseconds. And that's it. So this is the safe environment, right? So it's only 100 milliseconds and there are no errors. Calling it with Hystrix, and it shouldn't really make any difference. But in a second, and while the benchmark runs, I will ask you a question. What happens if I increase the duration to 2 seconds? What do you think? Yes, so the coin goes to you. I would really like to toss it in, but can you pass the coin to you? Okay, so the answer was that all requests will fail. Let me first analyze what happened here. So, well, nothing really happened. We have no failed requests. And we have response time of around 100 milliseconds. So nothing really interesting here. So what will happen now if I increase the duration to 2 seconds? So the system responds on average for 2 seconds, in 2 seconds. Now, if you remember, and that was a very good answer, if you remember, the default timeout in Hystrix is 1 second. So after a second, Hystrix kind of assumes that the system we're connecting with is down or something bad happens with it. So what happens there? And someone said that all requests will fail. But what I want you to actually focus on is the response times, not the error rate.
Around 1 second.
Around what?
Around 1 second.
Around 1 second, because the timeout is applied after a second. And that would have been a good answer if it was in Hystrix, but we'll see in a second. So no con for you yet. Exactly. So this one goes to. Okay. Watch out because it's quite heavy. Great. Okay. So let me just run it. So we have a very large latency of 2 seconds, and it was much faster than I expected. I wasn't really surprised, but hey. So this is interesting. 95% of the requests were actually faster than 16 milliseconds, even though our system responds within 2 seconds and the timeout is 1 second. So something fishy happened here. And this is this mechanism I was explaining to you called circuit breaker. Yeah, thank you. So let me just quickly browse through the logs to show you how it looked. Yeah, so what it says, runtime exception, Hystrix circuit short-circuited and is open. We'll get into that and I'll explain what that actually means. But Hystrix figured out that not only our system is unhealthy and it should apply a timeout, so we don't wait 2 seconds, we wait just 1 second, but also because the timeout occurred so often in the last couple of seconds, we should actually assume that the underlying system is entirely dead and we are no longer even calling it. Every time someone tries to invoke this command, where is it? Here. Every time someone tries to invoke this command, we just forget about it. Rather than calling this code, we immediately throw an exception saying that the circuit breaker is open. And this way, we are actually like cutting off this external system. We know that it's broken and we don't bother. We are not calling it, we're just failing fast, failing immediately, which is the core principle around Hystrix. Okay, everything clear so far? Okay, so let's have a couple more experiments. What will happen now if I go back to 200 milliseconds? Remember, Hystrix thinks that the system is down. Remember? As far as Hystrix is concerned, our external system responds too slowly, so it doesn't even bother calling it. Because, hey, it's down, so I'm not going to call in anyway. However, it's not as dumb as, just waiting for restart, because you might think that it just goes one way and it thinks that this external system doesn't work. So now you have to restart our application so that it has a chance to call it again. That's not the case, and we're going to explore it in just a second, but look what happens. Okay, so I'm running the benchmark, and now it's much slower. So somehow it again calls the external system, even though just a second before it thought that the system is down. So there must have been some magic again that makes sure that Hystrix at some point in time retries or makes sure that maybe the underlying system actually works. So we'll explore it in just a second. I will interrupt it, and as you can see, completed request failed quite a lot of them. Let me just try again to have clearer results. Let me start here. Yeah, now we have no failed requests. But we'll see in a second why is that and what happened. And you see that the response times were around 200 milliseconds. So everything is back to normal. Hystrix figured out that everything is fine. Okay, and everything is fine for you? Everything is clear? So we saw some mechanism. We see that something is happening under the hood from the engineering perspective, because all we have is logs and metrics. So let's look at the circuit breaker, which is, as I said, again, the core part of the actual Hystrix. So the configuration of the circuit breaker is actually quite advanced. Let me just browse it a little bit. So I'm going to tell you a story how it works. So we have a command, browsing here. We have a command that has a name and it belongs to a group. That doesn't matter. And we can control a thread pool, and we can control what is something that is called a statistics window. So for this command, Hystrix is going to collect the last 10 seconds of statistics. Imagine a sliding window that goes through time, and every time you execute a command, there is 10 seconds of the last statistics measured. By statistics, I mean how many times a command executed, how many times it failed, what were the distribution of response times, and so on and so forth. So we have 10 seconds of statistics. Within that window, when the circuit breaker is enabled, and by the way, everything I show you here are defaults, so you don't really have to put all of these are defaults, just to show you what's the configuration possibilities. So we have 10 seconds of statistics, and we have circuit breaker enabled. If there's more than 50% of failures, so if more than 50% of commands fail, and there were more than 20 executions in total, so more than 20 commands were executed in these 10 seconds, and more than 50% of them failed, then the circuit breaker trips open. And this is the state at which you no longer call the external system because you consider the external system dead. However, it would be really dumb if this state was taking place forever. So we went with a circuit breaker from the closed state, and when it's closed, everything is normal. We went to the open state. However, it cannot last forever. So what Hystrix does is after 5 seconds, it goes into something that is called a half-open state. A half-open state is really interesting. In that state, the first invocation, the first request to actually be executed, is not stopped on the circuit breaker. It's actually being executed. This is like a sample or like a probe. So we send a single scout that is supposed to make sure that the underlying system is still dead, or maybe it's alive at the moment. All the other requests in the half-open state are again like bumping off the circuit breaker, and we get a fail-fast behavior. So for all the requests, we still get this exception that the circuit breaker is open and I'm not going to call your command. However, a single command is actually sent to the external system, trying to figure out whether that system works or not. If the single scout, if the single sample succeeds, the circuit breaker is closed again, and we are back to business. We are again calling the external system. If the sample failed, then nothing changes. We go back to the open state, and we wait another 5 seconds to send another scout, another sample. Is that clear? How it works? Cool. So this is circuit breaker. This is the mechanism that actually Hystrix provides. This is the core feature, and it turns out to work quite well. Okay, I'm going to show you a couple of more parameters, and then we'll come back to the demo. So we have a pooled command. So I told you that there's an underlying thread pool associated with every command, or every command group actually. A group is signified here with a name. As you can see, the API is quite cumbersome and it's quite verbose. They say that, I mean the whole API, not just this part, they say, and by they I mean Netflix, who implemented Hystrix, they say that this is by design so that you really pay attention to what is being surrounded by Hystrix command and that you really pay attention to the parameters. However, there are some libraries that are actually wrapping Hystrix and making it much easier to use, for example, using annotations or aspects. Okay, but back to the actual slide. We have a thread pool for this command group, and this thread pool has at most 20 elements in the queue. So this is the maximum length of the queue of tasks, and the queue is only used if all the threads are already occupied. Or sorry, the actual parameter is 15. This is just like implementation detail, but this one basically tells us how many tasks are allowed to wait for a thread pool. And the size of the thread pool is 4, which means we allow 4 concurrent commands to execute. This is the parallelism concurrency level. And if all 4 threads are occupied, we allow at most 15 elements in the queue. This 20 is an implementation detail. I can tell you later why are there 2 parameters. So you have full control over the thread pools, and this is basically it. Okay. I can tell you later a little bit about semaphores, but I'm going to show you first a so-called statistics stream. So Hystrix has a built-in statistics servlet. This is basically a servlet that when you connect to it, it pushes the data on you regarding all the statistics that are collected by Hystrix. And Hystrix has to collect quite a lot of data. It has to know how many times every single command was executed, what was the error rate, what was the time distribution. It has to have all this information about every single thread pool. So this is a really valuable information, and it would be really selfish from the Hystrix side if it didn't expose this data. So I have this application already running here. So let me show you how it looks. I can actually connect to this stream because my application exposes it. It's optional. It's just a servlet. You can install it or not. It's your case. So this is the stream. So I'm connecting to my application, the one that has safe and unsafe endpoints, remember? So this time I'm using Hystrix stream, and this is just a servlet. Again, it's built in. And if I connect to that guy, it actually starts emitting quite a lot of stuff. You don't see it, but if I make this insane small font and run it right now, you can actually see that it just keeps pushing JSON data on me. And this data, I know you can see it, I just wanted to show you that it actually is there. And this data contains a lot of valuable information. For example, this is our command, /save. This is how we named it. And if you look carefully, I'm wondering if I use HTTP rather than curl, whether it would be formatted better. Or not? No. So let's go back to curl. So this is the command /save, and if you look carefully, for example, here you have latency distribution. So here you have distribution of execution times for every single percentile. It's 0 because these statistics have just 10-second duration, so we didn't invoke this endpoint in last 10 seconds, so you don't really see anything here. However, you do see information like, well, circuit breaker force open or the circuit breaker state. Quite a lot of data. You can actually go through it and see what it provides. All the statistics that you would ever want to have from Hystrix are here in this JSON. So it's relatively simple to build some sort of a dashboard, and I'm going to answer your question from the very beginning about WebLogic in a second. So all this data you have here, you can actually build a simple JavaScript dashboard that consumes this JSON data and shows some really nice graphs, samples, whatever. You can plug it into monitoring system, and if you have too high error rate of some command, this can trigger an alert and so on and so forth. And this is just being streamed for you immediately, and this is truly real time. So as I said, you can build quite cool dashboards on top of this JSON data, but you don't have to because one is already provided for you. So this is the actual Hystrix distribution. There's a component called Hystrix dashboard. It's very lightweight. It's actually almost only JavaScript. So I'm running it using Gradle. I'm running the application right now just to show you that it's actually there and it actually runs. So it will take a little bit, so let me talk for a while. So what this application does is that you paste the address of this stream. So you put this address into this application. It's going to connect to this stream, start consuming the data, and show you some really cool streams. And we can actually explore Hystrix quite a bit just by looking at these dashboards. Yep. I think, let me think about it. I remember I was actually exporting these statistics to Graphite, I think through JMX, so you have all sorts of features. But yeah, that's a good question, which deserves this little, I'm not going to toss it. You have one? Okay. Okay, cool. So the dashboard is here. Let me just quickly start it. It's localhost 7979. It's an entirely different application from the one we were trying in a moment. This is how it looks. It's provided for you, so you can tinker with it and do whatever you want. So now I'm pasting the address of my application. So it's, I think I need HTTP localhost 8080/Hystrix stream. So this is this address that was like vomiting with JSON in just a second before. So starting it right now. And we have some dashboard. It's entirely written in JavaScript. It shows some information, and in just a second, I'm going to explain you what all these numbers actually mean. So you have zeros all the way down, and it looks like a static image at the moment. So let me run a benchmark. Let me run a benchmark right here. So, okay, running /safe with a duration of 200 milliseconds. And /safe is one of our endpoints that is guarded by Hystrix. So nothing happens here at the moment. Can I actually show you two windows? Would it be cool? Yay, okay. So I'm going to start the simulation. I'm just going to press enter at some point, and I want you to look at the dashboard in the background, and you will see how it behaves when I start the benchmark. So it started, and yeah, I mean, there was like 100 milliseconds of delay or something, and I immediately see quite a lot of data on the dashboard. So now it's time to at least explain what the green one is. It's the number of commands in last 10 seconds, number of successful commands in last 10 seconds. And that's about it. We have some statistics here, and we also have the statistics related to a thread pool. So how many threads are utilized? The thread pool has 10 threads, and 5 are active. Why 5 threads are active? Because that's the concurrency level we set up here using -c parameter. And by the way, I just stopped the benchmark, and immediately on the dashboard, you see that it goes down. The purpose of this green little circle here would become obvious in just a second, but basically the size of the circle represents the volume of requests. So the bigger the circle, the more requests we have. So now let's go for something fancy. Nothing happens here. It's just completely flat at the moment. So now what do you want to see first? Error rate, of course. So error rate of how much? 0.3. So 30% of the requests will fail, which is less than this threshold. Of course, this is all probabilistic, but 30% error rate is still not enough to trigger this circuit breaker mechanism. So it's flat at the moment, starting the benchmark, and immediately you see something's going on. The color of this little thingy is actually slightly different. Maybe you don't see it, but it's more red-ish. And this indicator, the red one, shows you how many requests failed. So how many requests ended up with an exception. However, the circuit breaker is still closed, so we still keep calling the external system because it is not considered to be unhealthy. The error rate is quite big, 30%. And by the way, this is exactly what we set up, 33, 30 something. It's almost exactly what we set up. But still, this is not enough to trigger the circuit breaker. Okay, so obviously we're gonna increase the error rate now from 0.3 to 0.8, just to be, yeah, 0.5 is tricky because I'm gonna talk about it later. So 0.8, nothing happens yet. I haven't pressed enter, so I'm pressing enter right now. And here we have it, okay? So, whoa. So, you know, I have glasses since I was 10, but even if I take them off, I still see that something wrong is happening on production. So what's going on here? Oh, you see, as though the circuit became close. No, the benchmark is done. Yeah. So the benchmark was really, really fast. So instead of 1,000, let's make it 1 million. And the reason why it was so fast is was already explained to you, because the circuit breaker became open, so all the requests were failing fast. The pattern is named failing fast. That's why it was so fast. But let me just go through it again. So previously we had like, I don't know, 20 requests per second. Now we can handle da-di-da-di-da. Let me just wait for it to stabilize. So what was happening in the beginning, that was like green, red, was that Hystrix couldn't figure out whether the external system is working or not, because 80% is not 100. So at some point in time, it sent this scout, this single sample, and it actually succeeded. Oh, this happened right now. So when the single request succeeds, it considers the system to be healthy. But it's not really, so it quickly trips open again. So you have this simple state diagram where the system goes from closed to open. And if I actually go for 100% error rate or 99%, see it? Yeah, if I go for 99% of error rate, then it will be really, really stable. Stable in its unstableness because the external system doesn't work. But again, we get 100% error rate because every single request fails on the circuit breaker. And again, looking at these numbers, The green is 0. None of the requests succeeded. Even 1% because the circuit breaker is open. So none of the requests succeeded, and 10, 11,000 of requests were were stopped at the circuit breaker. This is not considered a major failure. It's actually a way to protect us from a major failure. We know that this external system doesn't work. We cut it off, and we continue the business as usual. And what's really interesting is that now we don't have 20 requests per second. We now have about 1,000. And if I increase the concurrency, we would actually get more. And this is really cool because our system really fails fast. And I want to ask you, and this deserves a coin, why do we have a number 2 here almost all the time? Can someone explain? Yeah? They couldn't fail anyway because the circuit breaker is cut off, so you don't even call. Yes, exactly. Okay, this one goes to you. So every 5 seconds there is this sample, this scout that actually tries the external system and makes sure that it's still broken, or maybe it's not. And since the statistic window is 10 seconds, remember it was one of the parameters. Since the statistic window is 10 seconds. So every 10 seconds we have about 2 samples being executed, and both of them actually failed. Okay, what else can we try? I'm going to stop this because it's going to burn my CPU. You want to see it? I don't have any statistics. Let me just run it again. You'll see that there's like a lot of traffic on the CPU. I have 8 cores, and all of them are not really that much saturated, but something's going on. But this time, the error rate would be 0. However, I'm going to increase the duration to 1100 milliseconds. So this is above the 1 second timeout. So what happens now? Excuse me? Okay. Yeah, it's fine, I think. Okay, let me just start with 110 to clear things up. So this is the healthy system, right? It actually calls the underlying system. The circuit breaker is closed. Everything is fine. And now I increase the latency to 1,100 milliseconds. And this is flat at the moment. Let's just run the simulation. And what happens here, another number is shining up, the orange or the yellow one. And this is the number of requests that timed out. There aren't that many of them because the thread pool is not that big. However, it leads to pretty much the same result. If the system is not responding within a second, it's actually exactly the same thing as if it was returning an exception. We consider the system to be broken. It doesn't matter if the system is returning errors or the system times out, it's broken. And I think there's going to be quite a nice background. Circuit breakers are actually a good thing for both sides, for the client and for the server. For the client, we already discussed that. Since we are not constantly calling an external system that fails, we are protecting from the failures in that system, especially from high latency. So rather than waiting a second every single time, we're just saying, okay, I give up, I'm not calling you anymore, apart from these 1 or 2 samples, because I know that you're having a hard time. However, it also gives a little bit of fresh air to the server, to the guy that we are actually calling. Because imagine he's just having a really big garbage collection, or maybe it has a queue of millions of tasks and it just has to process them. And obviously the system is going to respond in, the response times are going to be bigger. So just by using a simple retry and just poking and requesting that external system, we are not doing anything good either to us, because it's not going to work anyway, we know that, but also it makes it harder for this external system, the server, to recover, because rather than giving it some time to recover, we are just sending more and more and more requests. So what will eventually happen is that external system will collapse, and probably we will collapse as well, because we cannot wait that long. So what circuit breaker does for the external system is that it gives him like 5 seconds or 10 seconds of extra time, and in that time that external system can actually recover. It can actually handle all the pending requests, or maybe restart, or maybe finish with garbage collection, whatever. So this is quite useful for both sides. Okay, let me just stop it right now. And again, I stop the benchmark. Immediately you see a change on the dashboard. So this is truly real time, yeah?
statistics. The first one is timeouts, and the third one is fails. So what is the second?
Okay, so I'm actually gonna. First of all, they are explained here with and color coded. But okay, green one was explained. So this is the number of successful requests per second. Let me just do something useful in the meantime. Starting something. So this is the number of successful requests. This is the number of requests that bounced through the circuit breaker. So the circuit breaker was open. How many requests were rejected for the sake of that? This is the number of bad requests, and this is basically the mechanism in Hystrix that if you want to throw an exception from a command, it's always treated as a failure. Unless you're using exceptions for something different, some business exceptions, then you can mark them as bad requests, and they are calculated still as a success, even though they were a failure. Now, the orange one is a timeout. So how many requests were too slow? So if I go for 999, I think I should get some distribution. And there's actually a third parameter called standard dev. I don't remember how to use it, but this one will add a little bit of randomness to the response time. So if I'm not mistaken, yeah. So here you see that some requests were successful and some requests timed out. So we have some more real life distribution. This one is rejected, and the tasks are rejected from a thread pool. So if the thread pool is already saturated and we just keep sending more and more tasks, then the task is just eagerly rejected. So it's not a circuit breaker, it's a mechanism of a thread pool. It doesn't allow more tasks to be submitted. And this one is the number of failed requests. So that's about it. And the statistics of a thread pool, I think they are quite simple. Okay, does this answer your question? Okay, do you somewhat agree that it's almost as cool as in WebLogic?
The point was to have all the eggs in one basket.
Excuse me?
To have all the eggs in one basket.
Okay, cool. Yeah, it's like this saying that it's death by 1,000 dashboards, that every single thing has its own dashboard and you have pretty much too much monitoring. But yeah, so what I was doing, I was actually pushing this JSON through a little bit of glue code into Graphite or Grafana or whatever you prefer, and then I could see the statistics not for last 10 seconds, but for example for last 2 months. And it actually works. So you have real-time statistics here, and they are reflected instantaneously, but on the other hand, you can push these statistics into some database like Graphite, and then you have, if you know the tool called Graphite, that's really cool. And then you have these statistics aggregated for several days or months, so you can see what happened last Thursday with some particular command. You can group commands by external system or by method or whatever, depends on what suits you. Of course, circuit breakers are local to every command. So if one command fails and its circuit breaker tripped open, a second command can still be healthy. And it's up to you how you split your external systems into commands. Okay, everything clear so far? Some questions? Okay. Almost. So I have a slide for that. Let me just open it up quickly. So there's something called observable, and this is like a future but more powerful. It's also from Netflix. It's called RxJava, the library. It's like a completable future but more powerful. And if instead of calling execute, which is blocking, so execute will always return a string, if instead of execute you invoke observe, then you get an observable in return. And this is non-blocking, which means if you execute this command, this line takes no time to invoke. And what happens is that you can actually have two observables, observable 1, observable 2, command 1, command 2. And here you have two asynchronous commands running in parallel, and you can combine them, whatever. So this is very, very similar. Yeah, there was a question? Yes. Yes. What else? Okay, so the last thing I think we have time for is caching and collapsing, the two very nice things. So let's start from caching. The idea is that if you invoke the same command twice in the same amount of time, the second command is not executed, but it just waits for the first one to complete and returns the same result. Of course, this is not enabled by default, and what it does is that you have a command. You see this a plain old Hystrix command. But what it also gives you is the cache key. So every command can specify its cache key. Of course, this is not going to be a constant value. So imagine this is something like load person by ID command, and it actually takes int person ID as an argument. And then you use this parameter in a SQL query or something. So you are wrapping a SQL command somewhere. And in that case, your cache key would obviously be a person ID, right? So this is understandable. And now if two people, or two threads actually, invoke load person by ID at the same time, like this one, and if they both ask for the same thing, so for the person with ID 4, then the second command will actually wait for the result for of the first one. So you get a very simple caching here. This is not very powerful, but it's really, really simple, and it will allow me to explain the next thing. So is caching pretty much understandable? Yeah? It's concurrent hash map and just forget about it. If you need caching, if you need real caching, then go for real caching solution. How? No, it's actually by default just for a single thread. You can have it globally, but that's not the point. So caching is just an enabler for a feature I want to explain in a second. So this one, don't treat it as an enterprise grade thing. It's just there to have some really local and short-lived caches. But what I actually wanted to show you, and I think we have a little bit of time for that, is request batching. So you can try to run it at home. I would just show you how the code looks like. So imagine you have an interface that looks like this. So you have a ticker, which is basically the ID of a stock, and you can load a stock price using that ticker. So this can be, for example, IBM or Microsoft or Apple or whatever, and once you call it, you get a price of that stock. So that's like the simplest API ever. You're calling a stock market or a database or whatever, and having a name of the stock, like IBM, you get a price in return. So simple, right? Yeah. However, for performance reasons, or actually for throughput latency and you name it, reasons, you actually want to batch these requests. So if a single thread wants to ask for two different stocks, then it should use load many methods. And this one takes a collection of stocks, so it asks for IBM's, comma, Microsoft, comma, something in pseudocode. And what it gets in return is a map from a stock name to a stock price. So this is just a way of batch multiple small requests into a single big one. So it's like asking a database for multiple IDs rather than asking one ID at a time. Clear so far? Okay, so this is our API. And of course, it's really simple if we have a single thread and this thread knows all the stocks it wants to ask for. So we have a single HTTP request, and the single HTTP request wants to ask about IBM and Microsoft. Then we're just calling load many methods, and that's it. But what if we have two threads, two independent HTTP requests? One is asking for IBM, and the second one is asking for Microsoft. Oh, and there's a third request that is also asking for Microsoft. So the situation is that we want to ask for IBM, Microsoft, and Microsoft as well. So three concurrent requests occurring at the exact same moment in time. What's going to happen? So it would be nice to batch them. But now imagine what kind of code are you supposed to write to actually implement this? I mean, can you even imagine how it's going to look like and how many concurrency bugs you're going to introduce? Because you have independent requests, and now you are supposed to somehow organize the work between them so that if two requests occur at more or less the same time, then you should somehow join them, do a single request, and then split them. So that sounds pretty terrible. Of course, it's doable. It's not really that hard, but you have to code it yourself, and there are a lot of places where you can actually make a mistake. So what Hystrix does, it has a notion of collapsed command. So this is how it looks. And it's actually quite heavy with the code, but the idea is that If we execute two commands, just bear with me for a second. If you're executing two commands at more or less the same time, and these are commands of the same type, and this batching or collapsing mechanism is enabled, it will actually wait or kind of try to execute these two commands as a single one by combining them. So the mechanism is as follows. You have two commands, two individual commands. So it's stock, ticker, price, collapse command. And this command is not really meant to be executed by itself. What it does, it has a simple get request argument which says which stock do you want to execute. However, when there's more than one command executed at the same time, Hystrix batches all of them in a single, like a basket. So all of these commands are grouped together. And then it asks us to create a batch command. So it asks us to create a command that's going to return a map. So this big result. And the reason for this batch command, the existence of this batch command, is that it's supposed to collect all the smaller commands into a single bigger one, which is going to ask for all of them, for all the stock prices. And then when the result comes back, we have a result of type map. So we have all of them separately. So now we can take this map, this batch. So the reason being, if that works as well? It does? Okay. So the reason behind the batching is that rather than executing 10 commands that are doing more or less the same thing, you are actually executing just one command, one batch command. And when this batch command is ready, when it's done, there is yet another method that you're supposed to implement, map response to requests. And what it does, it takes the batch response and it pushes the response to every single small request that contributed to this one. However, this mechanism is a double-edged sword. Do you see a problem with this one? And I'm going to tell you this once again. So if many commands are executed at the same time, do you see a problem with this one? And this is the last question here. Yes, so it should, that there's a second point for you. Just grab it later, okay? So there is no such thing as commands happening at the same time. I mean, there is one command and it either executes or not. So what Hystrix does is that when the first small command appears, it's about to be executed, it starts a timer. And this timer is actually configurable. By default, it's 10 milliseconds. I have it here. Defined for 100 milliseconds. It starts a timer, and this timer waits for 100 milliseconds, hoping that another command will stop by for the same thing or for the similar thing. And within these 100 milliseconds, we are waiting for as many small commands as possible, up to 500. So this is another parameter. And when we reach 100 milliseconds, all these commands are grouped together. Hystrix asks us to create a batch command using this method, executes the batch commands, and then dispatches the batch response into all the small requests. However, and here's the danger, if our command is not executed frequently enough, so in this case, less than once every 100 milliseconds, then what we just did, rather than improving the throughput of our system, we just slowed down every single request by 100 milliseconds, because every single request has a 100 millisecond delay without any benefit. So use this feature in a very limited scale, only when the volume of the request is so big that it's actually worth it to collapse them. And then it works like a charm. Okay, I don't think we have any time for questions, so thank you very much.